Welcome to week 7 labs of supply chain design course. In this session, we have several questions to solve, and each of those covers teaching materials of week number 7. For the first question, we need to find the first iteration solution of the following transportation problem using simplex linear programming. In our problem, in our slide, we have 4 sources in Rotterdam, Wilhelmshaven, Bremerhaven, and Hamburg, and also we have 4 destinations in Munich, Salzburg, Prague, and also dummy destination. From each particular source to its particular destination, there is a cost of transportation at a particular price. For instance, from Rotterdam to Munich, the price per unit of products is at 40 something, 40 euro in this case. And for each source, it has a particular capacity of delivery. For instance, in Rotterdam, the capacity is at 30 tons, Wilhelmshaven at 15 tons, Bremerhaven at 20 tons, and Hamburg at 35 tons. And at each destination has a particular amount of demand. At Munich at 40 tons, Salzburg at 10 tons, at Prague at 35 tons, and dummy destination at 15 tons. And the task is that to find optimal allocation from which source to which destination, and therefore the cost of transportation is minimized. In order to answer the question, we have the following step. First, we need to formulate the problem into linear programming problem as follows. So, because we need to minimize the cost, and therefore the problem formulation will be cost minimization. We know from the figure in front of us that its transportation from particular source to particular destination has a particular unit cost. So 40 from Rotterdam to Munich, and therefore the index will be RM, meaning that Rotterdam to Munich. RS, it is from Rotterdam to Salzburg. WM from Wilhelmshaven to Munich, and WS, that is Wilhelmshaven to Salzburg. BM, that is Bremerhaven to Munich, and BS, that is Bremerhaven to Salzburg. And BP, that is Bremerhaven to Prague. HM, that is Hamburg to Munich, and HS, that is Hamburg to Salzburg, and HP, that is Hamburg to Prague, right? And for the constraints, we have several constraints as follows. That its transportation from a particular source to several destinations cannot exceed its capacity. For instance, here, in order to deliver from Rotterdam to either Munich or Salzburg or Prague cannot exceed 30 tons. And also for delivering products from Wilhelmshaven to Munich, Salzburg, and Prague cannot exceed than 15 tons, and so on. In addition to that capacity constraints, we have also demand constraint, meaning that in order to satisfy demand at Munich, and therefore XRM, that is delivery quantity from Rotterdam to Munich, and then also from Wilhelmshaven to Munich, and then from Bremerhaven to Munich, and from Hamburg to Munich, cannot less than the demand at Munich at 40 tons, right? And that also employs for demand satisfaction at Salzburg and Prague, okay? After formulating this linear programming problem, and then we have the following non-negativity constraint, that all transportation of products from all sources to all destinations cannot less than 0. And because the requirement is that we need to solve this by using simplex method, meaning that we need to convert this minimization into maximization problem. And therefore, all less than or equal to constraints can be converted into higher or equal to type by multiplying both sides by -1, right? And then we convert this minimization into maximization, and therefore we solve the dual form of the above problem by adding such variable si as follows. That first, for instance, here we have 30, we have 7 constraints, except non-negativity constraint. We have 7 constraints, 1, 2, 3, 4, 5, 6, 7. In order to convert this primal into dual, and then we have to use this right hand side of all constraints to be the coefficient of our dual objective function as follows. So, because first we need to convert all less than or equal to constraint into a higher or equal to, and therefore we need to convert this one by changing plus with minus, and also this with minus, okay? And also this one with minus, 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 and also here with minus. Here also minus, 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 and here is also minus. Also for this one, minus, 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 minus. And then we take the right hand side. So we have minus 30, minus 15, minus 20, minus 35, plus 40 this side, because it is already in a correct form with higher or equal to sign, and therefore it doesn't change, still 40, 10, and 35. And then we have this dual objective function. It is called dual objective function, right? And in order to compose constraints for these dual problems, and then we use the following. All right. First, we have x, because here we have xrm first, as the first variables, xrm, and then we find here again, is there any srm here? Yeah, srm here, and therefore here we have minus y1 plus y5 plus s1 equal to 40. It is coming from here. Let's say it is y1, it is y2, y3, y4. Here this equation put to be y5, y6, and y7. And therefore here we have minus y1 because we do not use anymore xrm as a primal variables, but we use y1, right? And plus y5, because here the same SRM here exists in y5, right? So y1 minus y1 plus y5, because there is no any change on this equation. So y1 minus y1 plus y5 equal to 40. So this 40, this each coefficient in this objective function becomes the right hand side of the constraints of dual problem, right? Here. And we do the same for other constraints by utilizing all primal variables here and convert into dual variables. For example here, SRS is minus y1 still, plus here we have XRS is y6, and therefore y1 minus y1 plus y6 should be equal to 39, because here XRS is equal to 39. Alright? Yeah. And we do the same for other constraint. And finally we have non-negativity constraint here. All dual variables from y1 to y7 should be higher or equal to 0. And then we can do iteration by using simplex method to find optimal solution from dual variables, right? And first This is our simplex tableau, the first simplex tableau, because we have one simplex tableau from each iterations, and we have to find first the simplex tableau from the original problem of our dual. All right, and for the first iteration and also for the following iterations in our simplex method, we have the following simplex tableau. In simplex tableau, we have several rows. For the first rows, it is some to identify what variables involved in our computation. In the first row and also column number 1 here, it consists of all slug variables starting from z, that is the value of objective function, and then slug number 1, slug number 2, and slug number 3, and so on until slug number 12. What is slug variables? Slug variables is a variable to be a quotient capacity in order to convert from inequality constraint into equality constraint, right? So for instance, in this case, we have in our primal, we have xrm plus xrs plus xrp less than or equal to 30. It is called inequality constraint. And in order to convert into equality constraint, we have to add something. It's called slug variables. Similarly, for dual problem, we have also slug variables. For instance, if we visit our first constraint y1 minus y1 plus y5, it should be higher or equal to 40. But in this case, we have to convert into equality constraint equal to 40, and therefore additional slug variable number 1 must be added into the equation. And that also employs for other constraints starting from constraint number 1 until constraint number 12 in this case, right? And all dual variables should be positive or equal to 0. And for the second the second rows contains information about it is about the coefficients of its variables in the objective function. For instance, here we have in the primal problem, individual problem, we have minus 30, minus 15, minus 20, and so on. And here we convert into 30 because actually all in simplex method we have to transfer, or we have to move all our right hand side variables into left hand side, and therefore it will be another constraints in our simplex solution. All right, in order to replace or to convert our objective function into additional constraint, and therefore we have to move all variables in the right hand side into left hand side. And in this case, we can convert this objective function as follows: that z equal to these variables from y1 to y7 into these variables 30 minus 30 y1 move to the left hand side, also for 15 y2 into left hand side, and therefore we have the following: 30 y1 plus 15 y2 plus 20 y3 plus 35 y4 minus 40 y5 minus 10 y6 minus 35 y7, and again plus z should be equal to 0. And we have the following set of numbers for our objective function. We have 30, 15, 20, 35, minus 40, and so on. 30, 15, 20, minus 35, minus 40, and so on. And we have also the value of our objective function equal to 0, because here we also have equal to 0, right? For the constraints, we don't have to change at all any numbers inside each of these constraints. So for instance, for constraint number 1, minus y1 plus y5 plus s1 equal to 40. And then here we have minus y1 plus y5 plus s1 equal to 40, right? And next, we have to find the leaving variables and the entering variables. In this case, we have y5 as a entering variables and s7 as a leaving variables. The reason of choosing those two variables is as follows. Let's see that we have here the coefficient in z row for y5 is minus 40, meaning that by entering y5 as a new variables, decision variables in our objective function, meaning that every additional 1 unit of y5 and then the profit can increase by 40. On the other hand, if we sacrifice slug number 7, that is S7, every time we replace S7, 1 unit of S7 with 1 unit of Y5, and then we will lose profit at 33, and that would not be a problem because by changing with Y5 we will have additional profit at 40. And therefore we choose here Y5 because it has the highest contribution per unit as compared to Y6 and Y7. So we put Y5 as a entering variables. Here is entering variables, right? And we have S7 should be as the first leaving variables, and then we call this S7 row as a pivot row. Okay, and we have to again change all cells, all values in each cells in this matrix by using Gauss-Jordan elimination. And another important rules for simplex problem is that every time we have here negative value, either y5, y6 or y7, and these numbers should be converted to be at least equal to 0, should be higher or equal to 0. The reason is that by having negative values, meaning that we have also a potential for having less profit by reducing at minus 40 or minus 10 or minus 35 per unit of production. Okay, and the regulation for operating this Gauss-Jordan elimination into our simplex tableau is as follows. That, for instance, here 30, the next value for the next iteration for 30 in Z row is that the current Z row minus the we call it here the pivot element times the here the current pivot row. And therefore, in order to have this Gauss-Jordan elimination work properly, and therefore every time we found that it's this, we call it pivot cells, if it is not equal to 1, and then we have to change this number equal to 1. For instance, here we have 5, and therefore here we should convert all numbers in this row by dividing those numbers by 5. Here, for example, 35 by 5. Here, 0 by 5, 0 by 5, 0 by 5, 1, minus 1 by 5, and so on. However, in this case, we have already 1, the value of pivot cells in our pivot row, and therefore we don't have to change these numbers, and Instead, we can use directly to calculate the new value in our Z row, right? And let's take an example for y1. So y1, the new y1 equal to the current y1 in current Z row, it is equal to 30 minus 40, and then times the current pivot row in this case, right? It is equal to 1, and then we have the following. Oh, sorry, minus 0, because it is current pivot row here equal to 0, right? So it is equal to 30. And let's check the result here. Yeah, equal to 30. And okay, let's try again for y3 here, because it changed from 20 to minus 20, right? And then for y3, the new y3 equal to the old y3 is called, it is equal to 20 minus here minus 40 times y3 here, y3 minus 1, okay, minus 1. So equal to 20 plus 40 equal to 20 minus 20, right? Because it is 20, yeah. 20 minus 40 equal to minus 20 here, okay? We do the same for other cells in Z rows, and we do the same also for other cells in other rows, and therefore we have the following number in the second simplex tableau that we will use to find the next values for pivot row and pivot column to operate in iteration number 2. And here the result for the first iteration, right? And hence, after we do the computation after several iterations, we have the following optimal value of our dual variables: y1 equal to 0, y2 equal to 9, y3 equal to 6, and so on. And the maximum number for z is equal to 3005, which is also the optimal solution of our primal problem. In order to prove this claim, and therefore we have problem number 2, to determine optimal solution of problem 2 using Excel solver, right? Okay, now let's work with Excel solver. We back to our problem. We try to solve the previous dual problem by using primal problem, and we would like to prove whether they have the same results in the objective function. Then we open our Excel solver. And afterward, we need to bring all of this equation into Excel solver. All right. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 12 variables: XRM, and then XRP, XRS, XRS, XRP, and then XWS, WM, XWS, and then XWP, and B, and finally H, right? H, B, x b s x b b, and we have x h hm x h s, and then x h p, right? Should be h. These are the variables, and then we have to compose our objective function. The objective function is equal to 40 times xrm plus 39 times xrs plus 35 plus 40 times xrp plus 35 times xwm, then plus 36 times xws plus 31 times wp plus 33 pm plus 43 times ps plus 42 times bp, and then plus 37 times hm plus 35 times hs, then plus 38 times hp. Okay, now we have a constraint formulation. Okay, before that we have to move all of this constraint to here. Oh, xrs plus xrm. So the constraint number 1, we have xrs plus xrs plus xrp. Okay, constraint number 2 should be xwm plus ws plus wp. Constraint number 3 is equal to xpm plus ps plus pp. Okay, constraint number 4, it is equal to xhm plus hs plus hp. Okay, and what next? Yeah, we have now demand constraint, that pm. Okay, constraint number 5, xpm pm plus ps plus pp. So here we have pm plus ps plus pp. It should be okay letter, and then 6 xrp, right? rp wp Okay, now we have the second. Okay, maybe it is better to put one by one. Right? So now we have the demand constraint that no, it is constraint number 5. It is for demand constraint that xrm plus XWM plus PM plus HM, right? Okay. Constraint number 6 says that RS plus WS plus PS plus HS. Now we have the last constraint, constraint number 7. RP plus WP plus BP plus HP, right? Okay, now we have constructed our objective function and constraint formulation, and we start calculating by using solver, and the goal is that to minimize the cost of delivery. So we have changed to minimize by changing all of these variables. Okay, and by adding first the first constraint, that C1, constraint number 1. Okay, for R, it should be less than or equal to 30, right? Constraint number 2, that is constraint number 2 is XRM, and then XWM, so it should be less than or equal to 15, right? Then we have the next constraint is XPM. XPM, the third constraint, should be less than or equal to 20. Okay, and then the next constraint is HM, that is constraint number 4, should be less than or equal to 35. And then we have demand constraint, constraint number 5, should be higher or equal to, here XRM 40. And the next constraint, constraint number 6, should be higher or equal to here equal to 10, right? XRS, yeah. Now we add the last constraint, constraint number 7, should be higher or equal to 35. And finally, non-negativity constraint should be added equal to 0. Okay, alright, so we have composed our problem in the solver parameter setting, and then we start solving the problem. And we know that objective function equal to 3005. It is equal to our previous computation here 3005. Okay, and then we have the following result, okay, from our Excel solver. Okay, let's do it again. Answer and sensitivity. Okay, answer number 1, we have objective function 3005, XRP equal to 15, XPM equal to 20, XWP equal to 15. So we can see here that not all networks are used in the final solution. Only few of them are used, just in order to minimize the cost of transportation, right? And here, what is the meaning of binding and non-binding constraint? Non-binding constraint meaning that the solution has some kind like slack variable, meaning that it is not used at the optimal, at the maximum capacity here. And for constraint number 1, for instance, if we look at here, constraint number 1, that XRM plus XRS plus XRP less than or equal to 30, meaning that the accumulation of XRM plus XRS plus XRP is not equal to 30. There must be at least higher or equal to 0 slug variables, and therefore it is called not binding constraint, right? And for binding, meaning that there is no any slug variables because the slug variable equal to 0. So yeah, this is the result. What about the sensitivity report here? We have final value here for informing us about the transportation quantity for each source to a particular destination, and also we have a reduced cost and also allowable increase and allowable decrease, meaning that for XRM we allowed to increase as much as possible quantity because in these networks there is no any transportation quantity used in our problem, and therefore it is allowed to increase as much as possible, right? And the reduced cost, meaning that if XRM increased by 1, meaning that the value of our objective function also increased by 1. Okay. And what about the next table here? We have constraints table. In the constraint tables, we have final value. We can see here that constraint number 1, the final value is 15, but the right hand side value is equal to 30, meaning that we have 15 as a cushion, meaning that the slug variable is not equal to 0. Indeed, it is equal to 15 because 15 plus 15 equal to 30. But for C2, the final value and the constraint right hand side is equal, meaning that the slug variable for this constraint equal to 0, right? Also for constraint number 3, number 4, number 5, number 6, and number 7. That also explain our previous table here, that constraint number 1, it is not binding because there is a slug variable used, so it is not used maximally, the transportation, even though the constraint states that XRM plus XRS plus XRP less than or equal to 30. It is not really equal to 30, but it is truly less than 30. Okay, and based on this sensitivity report and answer report, we can then construct our final network structure in our transportation. Alright, now let's go to the next questions. So we have to find also optimal solution, problem number 2, using modified distribution method. It is another method. Actually, there are 3 solution methods for solving our problem in our textbook to deliver products from 4 different sources to 3 different destinations. And the last method that I would like to discuss here is MODI. It's called modified distribution method. In order to solve the problem using MODI, and then first we have to find a feasible solution using northwest corner method. So what is northwest corner method? It is starting from north and go down until we finally arrive in the final destination in the west, right? From northwest, meaning that if we have here, if it is north, it is south, it is east, and it is west, and here is northwest, right? And therefore it started from northwest corner. Therefore the method is called northwest corner method. So the method is very simple. For instance, here we have 4 sources, we call it sources. Here we have also 4 destination, and then each source has its own capacity. Rotterdam has 30, Wilhelmshaven has 15, Bremerhaven has 20, and Hamburg has 35. and each destination has its own demand. Munich has 40, Salzburg 10, Prague 35, Dami has 15. So if, for instance, the capacity in all sources here exceed the demand in all destination point, then we have to add dummy variables here, just to equate between demand and source capacity. And for instance, here in Rotterdam we have 30, and therefore from Rotterdam we can deliver to Munich also at 30, cannot more than that, because the capacity of at Rotterdam is only at 30. And then we go down here, and Wilhelmshaven has 15, and therefore because the leftover demand at Munich is 40 minus 30 equal to 10, and therefore we have leftover 5 as a leftover capacity at Wilhelmshaven, and goes to the next destination, that is in Salzburg, because the demand at Salzburg at 10, and then we go down here 5 plus 5, and Bremenhaven left capacity is 20 minus 5 equal to 15, because the demand at Prague at 35, and then 35 minus 30 minus 15 equal to 20, and it will be met by Hamburg. So the leftover capacity at Hamburg is at 15. It will goes to dummy destination. Alright, so the total cost is calculated by multiplying all of this delivery quantity, 30 for instance here, times this. It is called unit cost, right? So 40 times 30, 35 here, 35 times 10, 36 times 5, 43 times 5, 42 times 15, 38 times 20, and 0 times 15, and we have 3,335 euro as the final first feasible solution. All right, and then we try to increase the quality of the solution by using the following method. In MODI, in order to find the updated solution from northwest corner, first we have to find multiplier variables for each sources and its destination as follows. So here in source column, we have Rotterdam, that is U, UI, U1, U2, U3, and U4. This cost column for calculating the multiplier variables. And the destination rows, we have Munich, that is phi 1, phi 2, phi 3, and phi 4. So for each non-empty cells in this northwest corner method table, and then we have the following. For instance, cell 1, 1, meaning that these cells U1 plus phi 1 equal to 40. The total transportation cost from Rotterdam to Munich is equal to 40. That is the first feasible solution by using northwest corner method, right? And then cell 2, 1, meaning this one, equal to 35. And then cell 2, 2, that is U2 plus phi 2 equal to 5. And then U3 plus phi 2 equal to 5 again. U3 plus phi 3 equal to 15. U4 plus phi 3 equal to 20, and U4 plus phi 4 equal to 15. And therefore we have the following. So we have to find each of these multiplier variables, U1, U2, U3, U4, phi 1, phi 2, phi 3, and phi 4 by using Gauss-Jordan elimination. And then, for instance, if we set phi 1 equal to 0, meaning that all transportation cost will be the responsibility of the transporter, in this case Rotterdam port, And therefore, if V1 equal to 0, if it is equal to 0, then U1 equal to 40, right? Equal to 40, right? It is also equal to 0, and then U2 equal to 35. Yeah, 35. And V2, because we have here equal to 35, and therefore, for transporting from source number 2, that is Wilhelmshaven, to Salzburg, we need additional 6, additional 1, I mean here equal to 1, and therefore V2 equal to 1. And we do the same for other variables, and therefore we find U4 equal to 38 and V4 equal to 0. Okay. Next, after we find our multiplier variables, and then we start seeking which alternative route that can reduce our cost, and therefore we have a method we call a zigzag method. What is zigzag method? Meaning that from here, let's say we have to find the best or the highest saving, because we would like to change our route from a particular route, and in this used cells in non-used cell in the current metric here. All right. Okay. Let's say here we have additional numbers, like here 2. It's called saving by changing, for instance, from any of these cells to these cells. We have additional saving at 2. Here we have additional saving at 0, 2 minus 3. Here is 4. Here also 4. Here is the highest at 9, and therefore we choose in the next iteration. And here is 1. And this is 3. And now the question is that how to find these values: minus 2, 0, 2, 4, minus 3, 4, 9, 1, or 3. And we do the following. All right. First, here we have cost at 40. Okay. And then if we move from any of the cells to these cells, and the cost down to 39, and therefore we have saving at 1. Okay. And then we have the following. If it is 40, right, plus 1 equal to 39, and then we have saving at minus 2. So it's called 40, right? This is the fee number 1, sorry, U number 1, plus fee number 2, minus the current cost at 1 and 2. So the 40 plus 1, right? And then minus 39 equal to 2, right? It is minus because we have saving at 2, meaning that we can reduce the total cost of transportation at 2. Therefore, it is minus. What about this one? U1 plus V3 minus C1 3 equal to 40 plus 0 minus 40 equal to 0. Therefore, there is no any benefit of using these cells. Okay, we still have benefit of using these cells. And what about these dummy variables? It is 40 plus, here we have minus 38, right? And then minus 0 equal to 2. Even if we move to the cells, we have additional cost at 2. Okay, and we do the same for other. For example, here 4 equal to 35 plus 0 minus 31 equal to 4. What about this one? Here we have 42 and then plus 1 minus 33 equal to minus 9. Okay, and therefore we finally choose these cells, and which cells to be eliminated by introducing these new cells. And therefore we have uh, the following zigzag method. Let's say here the highest resource or the highest quantity to be moved here is at 10. The lowest is at 5, right? And therefore we have to find the lowest here, that is 5. So here we have 5 minus y, here y, here 10 minus y, here 5 plus y. Why this minus, plus, and minus again? Because if we move 5 units from this cell to this cell, and then it should be minus y. Y is the moved quantity from this to this. And because we also move cells 5 or maybe any particular quantity from these cells to these cells at y, and then here also 10 minus y, because we would like to move also y unit from these cells to these cells and then to these cells in order to avoid these cells to be empty. Okay, and here 10 minus y, and then 5 plus y, and then here 5 minus y. Okay, and then after we do the same, we do this we call it zigzag method. Then we have the following matrix, that here we move from here to here, and this actually not anymore used because 5 units from these cells already moved to these cells. Okay, and then we have saving at mass s minus 9. Okay, and now we recalculate again the because it was 5, right? It was 5 minus 5, it is equal to 0. It is plus 5. It is equal to 10 minus 5 equal to 5, and it is equal to 0. So the new total cost will reduce from the previous value at 3290 into, oh sorry, it was 335 into 3290. 40 times 30 plus 35 times 5 here, because it was 10 minus 5. 36 times 10, because there is additional 5 units from these cells, and then here 33, because it has transferred a quantity from these cells to these cells. Okay, 33 times 5, 42 times 15, there is no any change with these cells, 38 times 20, and 0 times 15, and then we have 3290 as a new total cost. Okay, we do the same procedure for the next iterations. So for each non-empty cells with a delivery quantity less than 0, we calculate multiplier variable u1, u2, u3, u4, v1, v2, v3, and v4 as follow. And then we do the same procedure. All right, and again we would like to find a new alternative of routing, and then we have the following, that in the previous one we would like to sieve these cells transportation from Wilhelmshaven to Munich, to Wilhelmshaven to Prague. All right, and then we can again reduce the transportation cost from here. For instance, here we have, because we don't use these cells in this occasion, in this iteration, we use these cells, or these cells, and the least quantity will be here is at 10. Okay, so we move 10 to these cells. Here we have, yeah, okay, 10 to these cells, and then reduce 15. Here we have 5. Here we have additional 5. From the previous one it was 5, and then here we have 10 plus 5. Here we have 15. Okay, and then we have new total cost at 3 to 25. We continue further the computation until no improvement detected in the metric. Okay. All right. Now we go to the last questions. Question number 4. We have the network in our figure. Actually, this figure, yeah, should be figure number 2. Figure number 2. Right? And in figure number 2, gives the shipping routes from node 1 and number 2 to nodes 5 and 6 by way of node 3 and 4. So if we look at these networks, it is not anymore purely transportation, direct transportation from 1 and 2 to 5 and 6. Indeed, it passed through transshipment point 3 and 4. And in application, this kind of transportation networks is mostly used for minimizing the total cost of transportation, at the same time also by getting advantage of economic order quality, meaning that instead of directly ship from 1 to 5, it is better to stop for a while at station number 3, because station number 3 will consolidate products transportation from 1 and 2, and therefore will achieve economy of scale of transportation from 3 to 5 or 3 to 4 or 4 to 6. Okay, and the unit shipping costs are shown on the respective arcs, and the question is that develop the corresponding transshipment model, and we have to solve the problem and show how the shipments are routed from the sources to the destination. Okay, then we have to formulate into linear programming problem, and in this case we have actually 6 points, whether for it is like sources or destinations here. Okay, and in order to formulate the linear programming, then we have to consider a cost minimization, because each numbers in the arc here, for example arc 1 3, it is like cost for transporting 1 unit of one from 1 to 3. Also from here, from 2 to 3, the unit cost of transportation is at 3. From 1 to 4, the unit cost of transportation is at 4. Alright, and we have here arc variable x13, meaning that it is the transportation quantity from 1 to 3. From 1 to 3, it is x13. Here is x35, right? Here is x23, x14, x34, and x43. Here x45, x46, x24, and x56. Yeah, but not x65 is not exist in this network structure. All right, and we start formulating the objective function, that is 4x14, because from 1 to 4 the unit cost is at 4, and then 4x14 here plus 3x to 3 and plus 2x to 4. X to 4 we have 2, x to 3 we have 3, right, and so on until we arrive to x56, that is delivery from 5 to 6. And the constraints need to meet the following. First, it need to meet that the demand from 5 and from 6 at 100 and 100 also at point number 6 are met. And the second is that the supply to sources 1 and source and 2 are distributed as a whole, meaning that there is no leftover in either 1 or 2, right? And therefore we have the following formulation for constraint, that x13 plus x14 equal to 100, right? x13 plus x14 equal to 100, meaning that there is no leftover, there is no inventory in this problem. And x23 plus x24 equal to also to 100. x23, x24, oh sorry, this should be equal to 200, right? Equal to 200, right? 23 and 24. The next constraint is that we have to ensure that the demand at 150 from point number 5 and 150 from point number 6 are met. And then we have here x35 plus x45 here, x35 plus x45 minus, because the arrow is out from node number 5, minus equal to 150, right? And let's see, yeah, 35 minus, and also from node number 6 we have a demand at 150 by receiving products or units of production from nodes 5 and 4, right? So x46 plus x56 equal to 150, because there is no an inventory at this point, at this node number 6. And we have the following, and all are equal to. Next, we would like to formulate the objective function and also the constraints in order to calculate the optimal distributions for nodes number 1 and 2 to nodes number 4, 5, and 6. 3, 4, 5, and 6. Alright. And first, according to the figure in this problem, for distributing products from 1 to 3, it costs only $1 or €1 per unit, and therefore here we have x13 without any coefficient, because 1 times x13 equal to x13, and also x14 here times 4, because the there is a 4 monetary units per units of product transported from point 1 to point 4 here. Alright. And similarly for x24, the unit cost is at 2. 2 to 4 here, 2 to 4 is at 2, right? Yeah, 2 to 4 is at 2. Okay. And next we would like to formulate constraints. And the constraints is there are several constraints involved in this problem. At least one constraint stands for each variables or each nodes involved in this problem, and therefore there are at least 6 constraints. Constraint number 1 stands for node number 1, that is there is no any inventory should be available in each node, and therefore inventory at node number 1 is equal to 0, meaning that transportation of 100 unit to this node, meaning that node number 1 should be 100% transported either to node number 3 or node number 4. And in this case we have the first constraint, x13 plus 414 equal to 100. 1 3 here, transportation from 1 to 3 plus 1 to 4, it is equal to 100. Alright, so here we should not include coefficient 4 here. I have to revise this. It should not equal to 4 because it is only mass material balance, meaning that transportation from from 1, node number 1, to either 3 or 4 or both 3 and 4 should not should not higher or lower than 100 because no inventory available or permitted in station or node or point number 1. And also for here for node number for constraint number 2, it is constraint for node number 2. Any transportation for node number 2 to either point or station or nodes 3 and 4 is always equal to 200. There is no over or lower than 200 are not permitted. And the third constraint is the material balance at nodes number 3, that is x34 here, x34, x34, this transportation or to x and then plus x35, then plus yeah, so the entering material coming from 1 and 2 and also from 4 should equal to the leaving material from 3 to 4 and 6, and we have constraint number 3. Alright, here, and also constraint number 4, we have the same material balance at point or nodes or station number 6, right? And here, for instance, the third constraint saying that x35 plus x45 plus minus x56 here, x35 plus x45 and then minus x56 here should equal to 150. That is a demand at customer for nodes number 5, right? And also x46 and plus x56 equal to 150, meaning that 46 here, x46 plus 56 should be equal to demand at point number 6. And the next 3 constraint, the next, yeah, it is, so 2 constraint are material balance for nodes number 3 and number 4, right? So any entering material from nodes 1, 2 and 4 should equal to the amount of material out from nodes number 3 to 5 and then also to 4, right? Here. And the next constraint is a material balance for nodes number 4. And finally, the last constraint is a non-negativity constraint for all material streams for from one source to a particular destination. And we compose the following Excel solver parameter settings according to our problem formulation here. And I have composed as follows. Yeah, that the objective function, I follow the problem formulation here, and also the constraint I do the same, and from constraint number 1 to constraint number 6, and I also set the parameters using Excel solver parameter setting windows. And the objective is that I would like to minimize the cost of transportation, and it should be minimization problem, right? So the objective function here, B12 is the objective function, and the objective is to minimize the total cost of transportation by changing all variables x13 to x56 here. From x13 here, the flow variables is called the flow variables. From, for example, x13 from 1 to 3, 5 from 3 to 5, and so on. And the constraint, we have 6 constraints that B13, constraint number 1, it is like material balance at nodes number 1. C2 is a material balance at nodes number 2. Nodes number 5. And C3, it is material balance at nodes number 6. C4, it is material balance at nodes number 3. And C5, material balance at node number 4. All right, I can give explanation here that the first constraint is material balance. This material balance for node 1. It is material balance for nodes 2. It is material balance for node 5. Also material balance for node 6. Here, material balance for nodes 3. Here, 3. And it is not 4, right? And if I press the solver, then we can see here that x13 is 100, meaning the here is 100. I equal to 100. And then x23 at 200. 23 at 200. Here is 200. And 35, 300. Here at 300. And 5, 6 at 150. 5, 6, 150. Okay, that's all. No more other distribution nodes active, and the objective function is 2, 6, 50, right? And if we solve the problem and show how the shipments are routed from the sources to the destination, and then the new networks will be like this. That 1, it is 100, and then 2, it is at 200, right? Here both distribute to 3, and then from 3 to 5, and then 5 to both 6, and the demand for 5 itself 150, and 6 at 150. It is 150, 150. Here is 100, 200. Here as 300. Yeah, these are the new arrangement or the new networks for distributing product from both 1 and 2 to both 5 and 6. And we can see that 4 actually not used at all with regard to cost minimization of these transportation routings. All right. And if we look at the output of our Excel solver, we have final value at 2650, and also we have the variable value including the distribution of products from which to where, from what source to what destination points here. And we have also constraint table as I said before, bindings means there is no any slack variables used in this constraint, and there is non-binding constraints here. For example, x13, that is 100, that is it is not binding, and also x23, x13 and 23. Let's check here. X13 and 23, meaning that because it is not binding, meaning that this transportation at 100 and 200 are covered by the capacity of nodes number 1 and number 2 to nodes number 3, right? And also for other active routes, they are not binding, okay? And column number 1 explains about the location of the variables in our sheet, and the second column here, the name of the variables, and the third column is the final value, that is the quantity delivered from 1 to 3. And reduced cost here is that how much or how many we can change the value of the coefficient in our objective function. x13, for instance, we are not allowed change the coefficient at all, and therefore the value is at 0, meaning that we cannot increase the cost, the transportation cost, or decrease the transportation cost. And the allowable increase, however, is by 4, meaning that we are allowed to increase the ship product from 1 to 3 at 4 and decrease at almost infinity. However, at x14 in the second row of our table saying that the reduced cost is at 4. Why? Because actually from 1 to 4 there is no any distribution routes, and there is no any ship products from 1 to 4, and therefore the reduced cost is at 4 and the allowable increase is almost infinity because there is no any shipment from 1 to 4. And also for other rows in this upper table has the same explanation. What about the constraint? In the constraint table, we have location of the constraint. For instance, C1 is cell B13 and the final value is at 100. If we compare this final value with the constraint right hand side, we have a fact that they are the same, meaning that in this problem we have no slack variables. So all products are 100% shipped without any inventory. And the saddle price, this explains about the amount of resource that can be added into the constraint. For instance, constraint number 1, that is a constraint about the material balance at nodes number 1. That is, in nodes number 1 we have x13 plus x14 equal to 100, and we can change 100 by adding some units to be shipped from 1 to 3 or 1 to 4 as much as 1. That is the maximum additional unit from nodes number 1 to nodes number 3 or 4. Also for constraint number 2, the saddle price at 3, meaning that we could increase the value of right hand side. In this case is the ship quantity from nodes number 2 to nodes 3 or nodes number 4 at 3 units, right? But here there is no possibility to increase or decrease about the ship quantity from nodes number 1 and node number 2. And therefore, even though we try to increase the capacity of distribution from uh, from node number 1 to node number 3 and node number 4 as many as 1 units according to our report, sensitivity report, and from node number 2 as many as 4 units. However, it is not possible to what I want to say is that to increase the transportation from 1 to either 1 either to 3 or to 4, or from 2 to either 3 or to 4, because the available ship units from 1 is at 100 and from 2 is at 200, and therefore it is some kind of like useless to increase the availability of resources here, right? And therefore the allowable increase and allowable decrease is equal to 0, right? And yeah, that's all our today lab sessions. We have 4 problems. Those problems are related to solving distributions or transportation, both directly or indirectly, by implementing some kind of like cross-docking points, or in other words, we call it like transshipment points, to achieve economy of scale of distribution. And in question number 1, we try to solve the problem by using linear programming simplex model. And for the second, we would like to solve the same problem by using Excel solver to prove that our solution in simplex by using hands-on or manual solution is the same. We'll have the same results. And for question number 3, we would like to solve by using another method. We call it MODI, modified distribution method. And we have a conclusion that all those 3 solution methods produce the same result. And the last questions is related to transshipment problem, that we utilize Excel solver to find optimal solution of this transshipment problem. We have 2 suppliers and also 2 distribution centers and 2 demand point, or in this case we call it retailers. And we found that by using Excel solver, there is only 1 distribution centers or transshipment point can be used in order to minimize the transportation cost from 1 and 2, nodes 1 and 2, to demand point 5 and 6. Okay, this will be the end of our session today, and see you again in our next session. Thank you.